Kinetic molecular theory of gases. Gases are, as all matter, made up of particles. We're going to be using 5 postulates of the kinetic molecular theory applied to gases to imagine how gases will behave. First postulate, we need to think of these particles of gases as these tiny particles, high translational energy, meaning they move from one place to another a lot. When they move from one place to another, will travel in straight lines until they hit something. And generally, this postulate that we're assuming about gases will be true. A case where it might not be is if you have, say, I don't know, a planet, and you had a particle of gas in outer space. It would be moving in a straight line, but it does get affected by things like forces of gravity or, more likely, electrostatic forces as well. We're going to ignore those. We're going to pretend they just travel in straight lines. The second postulate that we're going to be using to think about these gases is that the gas particles occupy no volume themselves. They're going to be in a container, so the gas itself as a bulk substance will have volume, but we're going to pretend that each little particle here doesn't take up any space. And we know that's not true. We're just going to pretend it's true to make our lives easier. We know the particles do have some amount of space. You can imagine if that's a tiny particle right there, it does have a diameter to it. Even if it is a atom of helium, it's going to be very, very small. It's not going to take up very much space individually, but we're going to assume it takes up no space. The reason why is because we're essentially going to be looking at the volume of the container that the gases are in, and the pressure that those gases are affecting on that container as well. And that's going to be such a huge amount of space that the particles are in compared to the actual space themselves. So imagine a container that's like 1 meter in width. That's a pretty big volume, 1 meter, compared to the size of the particles actually in that volume. So we're going to pretend the particles have no volume because the number is so small compared to the actual volumes we're going to be measuring. The third thing that we're going to be assuming to be true is that collisions between particles are going to be perfectly elastic. So when one particle hits another, they're going to bounce straight off and they're not going to lose any energy when that happens. And essentially that's pretty easy for us to assume. We're not getting any complicated physics or anything like that. So this holds true for everything that we're going to be doing. We're also going to assume that particles have no attractive or repulsive forces between them, which from all of our work on polarity, we know that these particles may or may not be more or less attracted to each other. There's going to be a little bit of attraction, but if they're polar, like these molecules here, we know that there's going to be the negative end being attracted to the positive end quite a bit. We did all that work on polarity, but for gases, that force is going to be so small, we're going to neglect it completely. So we know it's there, it's just not going to have much of an effect on what we're doing. So while we're talking about gases, let's just ignore it. Also, we're going to assume that the average kinetic energy of a particle is directly related to its temperature. So we are assuming that if we add some temperature to these particles here, we're going to see a direct relationship to the kinetic energy of those particles. We're not going to worry about losing or gaining energy. We're assuming all of the energy from heat is going to go directly into the motion of the particles, which again, since we're not really getting into really precise physics, we can make that assumption. So these postulates describe what's called an ideal gas. It's a pretend, not a real gas, that works and behaves ideally. It doesn't get attracted to other particles. It doesn't take up very much volume. It doesn't lose any energy with collisions, or temperature gets created directly over to motion. All of that stuff doesn't happen exactly, but the differences are so small that we can completely ignore them. So we're kind of imagining real gases a little bit more simply than they actually are. And by doing so, when we talk about gases as if they were ideal gases, they follow these 5 postulates, it makes our calculations very, very simple. Essentially, by making these assumptions, we're going to be a little bit wrong, but so little that we don't really care. And it makes our lives a whole lot easier to assume all gases will behave as ideal gases.